Right now, like sitting quietly in your kitchen, there is a machine that is basically fighting a continuous high-stress war against the environment.
Oh, absolutely.
And I mean, we look at a refrigerator and we just see, a silent ice box, just this static piece of architecture where you put your milk in and later you take cold milk out.
Right. It's just part of the furniture to most people.
Exactly. But if you actually pull back the casing of a modern, large-capacity smart refrigerator,
Hmm.
well, that illusion of a simple passive box completely shatters.
Yeah, it really does. I mean, it is the absolute definition of a highly stressed, incredibly complex thermal management system.
Well, thermal management system, that sounds intense.
It is. We take these massive, French door models for granted because their primary job is to be totally invisible to our daily routine. But these aren't the rudimentary metal coolers from 30 years ago.
Right, they're not just metal boxes anymore.
No, not at all. They are intricate, highly engineered networks. I mean, they're packed with sensitive microprocessors, precision thermodynamics, and mechanical actuators that are operating under immense kinetic stress.
And that invisible stress is exactly why you're joining us for this deep dive today. We have this remarkably detailed service guide on the table, and it was published on April 1st, 2026 by a local Florida business called Appliance Repair Bradenton.
It's a fantastic document, honestly. So much detail.
It really is. So our mission here is to decode the hidden, complex life of the modern smart refrigerator. We're going to explore the silent environmental war being waged on your kitchen appliances every single day.
Which is happening right now, by the way.
Literally right now.
Yeah.
And we'll discover the specific mechanics of how you can protect what is, frankly, a massive financial investment. Because we usually only think about the internal workings of these machines when, we wake up on a Tuesday morning to find a giant puddle on the floor and $200 worth of groceries just actively thawing.
Yeah, which is the absolute worst time to start diagnosing a mechanical failure.
Oh, for sure. Total panic mode.
Right. And the stakes here go far beyond just losing some leftovers. We're talking about the sudden, catastrophic failure of a machine that costs thousands of dollars.
Plus the immediate loss of all the food inventory it protects.
Exactly. For anyone managing a demanding career or, a busy household, you simply cannot afford that level of logistical and financial disruption. Understanding the mechanics of these machines before they fail isn't just about curiosity. It's really a vital aspect of modern home ownership.
So let's start by looking at the machine itself. Before an appliance completely gives up the ghost and ruins your week, it actually tries to communicate with you.
It does. It sends out warning signs.
Right, it starts sending out these mechanical death rattles. But according to the Appliance Repair Bradenton Guide, homeowners consistently ignore these early symptoms. They mistake severe mechanical distress for just, normal quirks of an aging machine.
Which is a huge mistake.
Okay, let's unpack this, starting with the temperature imbalances. The guide highlights a specific scenario. You open the freezer, and it looks like an Arctic tundra. Just a massive frozen wall of ice.
Right, totally frosted over.
But then you check the fresh food section, and your milk is barely cool. So my question is, why wouldn't the whole unit just warm up if it's breaking?
Well, that's because of how the cooling architecture actually works. Most people assume, that the refrigerator and the freezer each have their own independent cooling sources.
Right, like two separate air conditioners or something.
Exactly. But in reality, the vast majority of these units only generate cold air in one place, and that's the freezer section.
Wait, really? Just the freezer?
Just the freezer. There is a component called the evaporator coil located back there, and it produces all the freezing air for the entire appliance.
So the fresh food section doesn't actually produce its own cold air at all. It's just borrowing it from the freezer.
Precisely. It's a borrowed air system. And the gatekeeper of that borrowed air is a mechanical device called the damper control.
The damper control. Okay.
Yeah, it is literally a small motorized door situated in the ductwork right between the freezer and the fresh food compartment. The refrigerator's thermostat constantly measures the temperature in the fresh food section.
So it's always monitoring.
Right. And when it gets too warm, it signals the damper motor to open that little door, allowing a fan to push freezing air from the bottom up into the top compartment. Once the target temperature is reached, the door closes.
Okay, so if the freezer is an icebox but the fridge is warm, that mechanical door has basically failed while it was closed.
Exactly. The damper motor burns out, or ice physically blocks the door from moving. So the thermostat in the fridge keeps panicking, just screaming for more cold air, which forces the compressor to run continuously to generate it.
Oh, I see.
But because the damper door is stuck shut, All that newly generated cold air is trapped in the freezer. It turns it into an Arctic tundra while your fresh food just spoils.
That makes so much sense. You aren't losing the ability to create cold, you're losing the ability to distribute it.
Perfectly said. Yes.
Wow. Okay, what about the puddles? The guide mentions finding water pooling right under the unit. I mean, the immediate panic is always that a pipe burst in the wall, but this guide points to something much more isolated.
Puddles are a classic sign of an interruption in the automatic defrost cycle. You see, frost naturally accumulates on those evaporator coils in the freezer.
Right, because it's cold.
Yeah, and to prevent the coils from turning into a solid block of ice, modern fridges have a defrost heater that turns on periodically just to melt the frost.
Oh, okay. I didn't know they had heaters inside them.
They do, and that melted water drips into a catch trough, flows down a specific defrost drain tube inside the back wall, and empties into a shallow pan at the very bottom of the fridge.
And then what happens to the water?
Well, the heat from the compressor naturally evaporates it right into the room.
Oh, I see. Let me guess, that internal drain tube gets clogged.
It gets completely clogged with food particles, dust, or even frozen condensation. When that happens, the melted water from the defrost cycle has nowhere to go. It backs up, overflows the catch trough, freezes on the bottom of the freezer compartment, and eventually leaks right out of the front door onto your kitchen floor.
That sounds like a nightmare.
It is. And the other culprit for puddles, of course, is a microfracture in the plastic water supply line feeding the ice maker.
Oh, yeah, the ice maker lines.
Yeah, those lines become really brittle over time and can develop these tiny pinhole leaks that just drip relentlessly.
So those temperature and water issues are, somewhat silent, but eventually the fridge will literally start crying out for help audibly.
Yeah.
The guide breaks down 3 very distinct noises. There's grinding, buzzing, and clicking.
All very bad sounds.
Right. And a grinding noise makes intuitive sense based on what you just said. If the defrost cycle fails and ice builds up, the fan motor trying to circulate the air is going to start physically hitting that ice block.
Exactly. It's like a very mechanical, physical grinding.
But then there's the clicking sound. The guide emphasizes this one, and honestly, the analogy they use is incredibly relatable. A clicking start relay is like a car engine trying desperately to turn over on a cold morning, but just failing to catch.
What's fascinating here is the precise electrical sequence causing that click. The compressor is this heavy-duty pump that circulates the chemical refrigerant through the system. I mean, it is the literal heart of the cooling process.
Right. Without it, nothing works.
Exactly. But that compressor requires a massive instantaneous jolt of electricity just to overcome inertia and start spinning. The start relay is the electrical gatekeeper responsible for delivering that jolt.
Okay, so it's like throwing a really heavy electrical switch.
Yes, exactly. And inside that relay are actual physical contacts that snap shut to allow the high voltage to flow. Over thousands of cooling cycles, the electrical arcing burns and pits those tiny metal contacts.
So they just wear out over time.
They do. Eventually, they become so degraded that even though the relay mechanically snaps shut, which produces that audible click you hear in the kitchen, the electricity cannot flow across the damaged metal.
Oh, wow. So the gate opens, but the power just doesn't make it to the compressor.
Right. And without the compressor, the refrigerant stops flowing, and the entire thermodynamic process halts instantly.
That is wild. And what if the problem is the exact opposite? Like, what if the motor is just running constantly? The guide mentions constant motor cycling. To me, that is like forcing an employee to work 24 hours a day, 7 days a week without a single break. Eventually, the physical exhaustion is going to cause a total collapse.
That's a great analogy. The underlying thermodynamics of a constant run cycle are brutal on the machinery.
I can imagine.
Yeah, a refrigerator is designed to cycle on, aggressively reject heat from the interior, reach a stable low temperature, and then shut down to rest.
It needs a break.
It absolutely needs a break. If the compressor is running nonstop, it means the system is experiencing thermodynamic suffocation. It is desperately trying to reach a temperature equilibrium that is mechanically impossible to achieve.
Impossible why? Like a broken part.
Maybe because the refrigerant has leaked out, or the condenser coils are insulated by dust. The compressor is a mechanical pump generating its own immense heat. Without rest periods to cool down, the internal windings will literally cook themselves to death.
Yikes. Which brings up a crucial question. Why are these machines under such intense stress to begin with? I mean, they sit inside our houses.
Indoors.
Yeah. This shifts our focus from the internal mechanical failures to the external environmental forces attacking the appliance. The guide from Appliance Repair Bradenton places heavy emphasis on the geography of Manatee County, Florida. They talk about battling incredibly high humidity and soaring summer temperatures.
Geography and local climate dictate appliance lifespan just as much as the engineering of the machine itself. In a place like Bradenton, the ambient environment surrounding the kitchen is inherently hostile to the goal of the refrigerator.
Here's where it gets really interesting, because I have to challenge this premise a little bit. We usually think of our modern homes as perfectly sealed, climate-controlled bubbles.
Right, we have the AC blasting.
Exactly. We have heavy insulation, our central HVAC systems are running constantly, and the doors are shut. Surely opening the refrigerator door for the 5 seconds it takes me to grab a soda doesn't invite enough of that Florida heat inside to cause structural damage to the compressor. Are you really telling me that casual browsing is an operational battle?
I am. It is absolutely an operational battle, and the reason comes down to the physics of latent heat and vapor pressure.
Okay, break that down for me.
Well, when you open that heavy door, the cold, dense, dry air inside the fridge literally falls out onto your kitchen floor. To replace it, a massive volume of ambient air rushes in. Now, even with your home air conditioning running, the air in a Florida kitchen holds a significantly higher volume of water vapor than the air inside the fridge.
So it's not just about the temperature of the air rushing in, it's about the water suspended in that air.
Precisely. When that warm, moist air hits the cold internal surfaces of the refrigerator, the water vapor immediately condenses into liquid droplets. This phase change, going from vapor to liquid, releases a massive amount of thermal energy called latent heat.
Wow. So the fridge doesn't just have to cool down the new air, it has to actively fight the thermal energy released by the water condensing on the plastic walls.
Yes. The system has to aggressively kick into high gear, running the compressor much longer and harder than normal to reject all that newly introduced latent heat and pull the moisture out of the air to prevent mold.
That sounds exhausting for the machine.
It's a violent thermodynamic swing. Every time you open the door, you aren't just letting in a little warmth, you are forcing the compressor to absorb and expel a heavy thermal load. Over years, the kinetic stress of those constant aggressive recovery cycles dramatically accelerates the wear and tear on the internal mechanics.
That completely changes the context of standing in front of an open fridge trying to decide what to eat. You're literally watching the lifespan of the compressor tick down.
You really are.
But heat and humidity aren't the only local adversaries. The source also highlights summer thunderstorms in Bradenton.
Oh yeah, electrical grid volatility is a massive, silent killer of modern appliances. Those intense afternoon thunderstorms bring lightning strikes and grid fluctuations that cause sudden, violent power surges.
But older fridges survive storms just fine. Why are the new ones so vulnerable?
Because a refrigerator from 1995 was mostly just mechanical switches and heavy-duty wiring. A modern smart refrigerator is essentially a complex computer server that happens to keep food cold.
Oh, that makes sense.
Yeah, they are governed by delicate electronic control boards packed with microprocessors, EEPROMs, and tiny capacitors. When a massive voltage spike hits the house, it bypasses the heavy mechanical components and instantly fries the microscopic silicon pathways on those logic boards. It literally melts the brain of the appliance.
Okay, so now that you, the listener, understand exactly how the environment is attacking the machine and how the machine tries to signal its distress, how should we actually react?
Good question.
Right, because the Bradenton Guide provides a triage matrix. It translates all this complex thermodynamics into an actionable game plan, answering the ultimate homeowner dilemma. Do I attempt to DIY this repair, or is this a complete disaster waiting to happen?
You have to know your limits.
Exactly. Let's start with the stuff they claim is totally safe for the DIY enthusiast. Vacuuming dirty condenser coils every 6 months. Does taking a shop vac to some dusty coils underneath the fridge really save that much money, or is that an exaggeration?
It is not an exaggeration at all. It is the single most important piece of maintenance you can perform. The condenser coils are basically the radiator of the refrigerator.
Okay.
Their entire job is to expel the heat that the compressor has pulled out of the internal compartments. When those coils get coated in a thick layer of pet hair and kitchen dust, that debris acts as a thermal blanket. It insulates the coils.
Ah, so the heat can't escape into the room.
Exactly. The heat transfer coefficient plummets. Because the heat cannot dissipate efficiently, the compressor has to run significantly hotter, and for much longer cycles just to achieve the same internal cooling.
Which costs more money.
Oh, absolutely. You will see a massive spike in your monthly energy bills as the machine struggles against that thermal blanket, and eventually the compressor will suffer a catastrophic thermal overload and seize up entirely. 30 minutes with a vacuum brush prevents thousands of dollars in damage.
The other safe DIY tasks follow a similar logic. Flushing that clogged defrost drain tube we talked about earlier with warm water, which takes about an hour. Or replacing worn rubber door gaskets, which only takes 20 minutes. If those gaskets are torn, you're constantly leaking that latent heat we discussed right into the fridge.
Notice the pattern here. All of those safe DIY tasks are external maintenance.
Right.
You are manipulating the airflow, clearing external drainage, and sealing the perimeter.
Yeah.
You are never breaching the sealed internal systems.
Right, which brings us to the absolute professional necessities. The guide lists faulty compressors, which take 2 to 4 hours to replace, and defective electronic control boards, taking 1 to 2 hours. Trying to diagnose and solder a control board yourself sounds like trying to perform your own root canal.
It's a terrible idea.
But I have to ask, with the sheer volume of YouTube tutorials out there, is the risk of voiding a warranty or causing further damage really that high for an ambitious DIYer?
This raises an important question about the legal and physical realities of modern appliance engineering. The risks are astronomical. Let's look at the compressor first. To replace a compressor, you must cut into the sealed refrigerant lines.
Which sounds dangerous.
It is. You are dealing with pressurized chemical refrigerants. Venting those chemicals into the atmosphere is a direct violation of federal EPA regulations under Section 608 of the Clean Air Act, which requires specific handling certifications. You physically cannot buy the chemicals or the brazing equipment legally without those credentials.
Wow, okay. And the control boards, there's no legal gas in those.
No, but the electrical risks are just as severe. These logic boards route complex AC and DC voltages to various sensors and motors. If a DIYer misdiagnoses the board or plugs a harness in backward, which is incredibly easy to do, by the way, they can instantly send 120 volts of alternating current down a wire meant for a 12-volt direct current temperature sensor.
Oh man, that sounds like a disaster.
The moment you plug it back into the wall, you hear a loud pop, and you have instantly destroyed a brand new $400 logic board and potentially started an electrical fire. The smartest maintenance a homeowner can perform is possessing the humility to know exactly where their competence ends and a trained professional's begins.
So what does this all mean? Let's zoom out from the specific wiring harnesses and thermodynamics and look at the entire home ecosystem.
It's all connected.
It really is. The source makes a compelling argument about the logistical and financial fallout when appliances fail. For you, the listener, juggling a busy career and a growing family, a broken appliance isn't just a mechanical failure, it is a massive disruption to your weekly momentum.
A huge disruption.
Yeah, the kitchen is described in the guide as a synchronized environment. When one piece of that machinery stops, the friction spreads everywhere. A broken washer halts the weekend hustle of cleaning uniforms for a tournament. A broken fridge means losing hundreds of dollars of carefully planned weekly meal prep.
It creates severe operational friction in the household. That is why the service guide emphasizes the logistics of repair just as much as the mechanics. Appliance Repair Bradenton prioritizes rapid response times, aiming for same-day or next-day service, specifically to mitigate that friction.
Because time is of the essence.
Exactly. They understand that every hour a refrigerator is down, the thermal clock is ticking on the food inventory.
They even carry common replacement components right in their vehicles to try and solve the mechanical failure on the very first visit.
Which is super smart.
But eventually, every homeowner faces a very stressful financial crossroads. Do you repair the broken machine or do you bite the bullet, drag it to the curb, and replace it entirely? I love that this source provides a concrete metric for this. They call it the golden rule of replacement.
It is a vital heuristic for avoiding the sunk cost fallacy. The rule states, if the refrigerator is less than 10 years old and the quoted repair costs less than half the price of buying a brand new replacement unit with similar features, executing the repair is the smartest financial decision.
Less than 10 years old, and the fix is under 50% of a new one. Why those specific numbers?
If we connect this to the bigger picture of appliance manufacturing, compressors and sealed systems generally have an engineered design life of roughly 10 to 15 years before mechanical fatigue becomes inevitable.
Okay, so that's the 10-year mark.
Right. If the unit is under 10 years old, the core architecture is still structurally sound. Regarding the 50% threshold, it's about capital allocation. If a new smart fridge costs $3,000, spending $800 to replace a logic board on a 6-year-old unit is a sound investment. You are amortizing the life of the appliance.
But spending $2,000 to fix it wouldn't make sense.
Spending $2,000 to fix that same fridge makes no economic sense whatsoever.
It highlights the immense value of having a transparent, local expert. You need someone who doesn't just want to sell you a new showroom model, but a technician who understands the specific environmental stressors of the Florida climate and the true financial math behind preserving a major household asset. Well, we have covered an immense amount of ground on this deep dive. We started by decoding those ominous clicking and constant humming noises, realizing that our fridge is desperately trying to signal electrical and thermal distress before a catastrophic failure.
It's talking to us.
It is. And we explored the physics of latent heat and how simply opening the door invites a wave of heavy humidity that forces the compressor into a violent operational battle. We navigated the triage matrix, learning why vacuuming coils is brilliant, but messing with logic boards is a financial death wish.
Leave that to the pros.
For sure. And finally, we armed you with the 10-year, 50% financial rule to help you navigate the economics of repair. Thank you for joining us as we unpack the surprisingly complex thermodynamics and hidden life of your kitchen appliances.
It fundamentally changes how you view the machinery operating silently in the background of your life. And I want to leave you with one final thought to mull over, building directly on what we discussed regarding the physics of air exchange.
Well, I'm ready.
Think about this. We learned today that every single time you pull open that heavy refrigerator door, a massive wave of hot, humid air rushes into the cabinet, releasing latent heat and forcing the compressor into an aggressive lifespan-shortening recovery cycle.
Right, the battle.
Which means the absolute biggest threat to the structural longevity of your expensive, highly engineered smart fridge isn't a power surge or a dusty coil. It might just be your own daily habit of standing in front of the open door browsing for a midnight snack.
Oh, wow.
It really makes you wonder, as these machines get more expensive and complex, how will future appliances be engineered to protect their thermal integrity from our own indecision?
Are they going to install biometric locks that only let you open the door if you know exactly what you want? Honestly, after learning how much kinetic and thermal stress they endure just to cool down the air we let inside, I wouldn't even blame them for locking us out. Suddenly that simple, silent icebox isn't so simple anymore. Until next time, keep an ear out for that clicking sound, and seriously, decide what you want to eat before you open the door.